for today. So the first speaker is Robin Kothari, who will talk about quantum distinguishing complexity zero-error algorithms and statistical zero knowledge.
Thanks for the introduction, Francois. All right, thanks everyone for coming. This talk is going to be about quantum query complexity, and specifically my talk's titled Quantum Distinguishing Complexity, Zero-Error Algorithms, and Statistical Zero Knowledge. Don't worry, you don't need to know what those things are. I'll explain some of that during the talk. My name's Robin, and this is joint work with Shalev Ben David, who's at the University of Waterloo. Okay, so let me start with a review of query complexity, because that's what this talk is going to be about. Query complexity is one of the simplest models of computation that you can study. And as is the usual game, there's some function that you're trying to compute on some input. In this case, the function is going to be a Boolean function, f, going from n bits to 1 bit. So the input is an n-bit string, the output is 1 bit. The input x, which is the n-bit string, will be written as x1, x2, x3 to xn. And these are the individual bits of the string. And the game in the model of query complexity is that you don't have access to this input string. The input string is known to somebody else, and you get charged for every bit of the input string that you read. So every time you want to know an input string, like you want to know what is the value of x3, you have to go and, let's say, open a box and read what x3 is. And every time you do this, you get charged 1 unit cost. So the cost model is how many bits of the input you read. And the goal in all of these query complexity models is to compute the function by reading as few bits of x as possible. So we want to compute f of x. So recall that f is known, but x is not known to you, and the bits of xi are the things that you're being charged for reading. And the different models in query complexity will differ based on what reading bits means, and also what it means to compute a function. Like, do you have to do this exactly? Can you do this with some error? Also, do you have quantum access to classical, and so on? And to be more concrete, in the classical setting, one way to think about this is you want to compute the function f of x using a circuit. In the quantum setting, you'll have a quantum circuit. In the classical setting, you'll have a classical circuit, while minimizing the uses of an oracle. And the oracle will be the object that knows what the input string x is. And that's the thing to which you submit an index I, and it'll respond to you with the value of the bit x of I. So formally, classically, you'll have an oracle that looks like that. It's an object OX into which you submit an index I, and it replies x sub I to you. Quantumly, you have essentially the same thing, except the classical oracle is not reversible or unitary, so you have to do a little bit of change to make it a valid unitary operation, but it's essentially doing the same thing as the classical oracle. And the quantum query complexity of a function f is just defined as the minimum number of queries you need to make to this oracle. So if you look at the circuit over here, maybe I shouldn't use the laser pointer. I'm going to use this. I hope this works. Okay. So if you look at the circuit over here, these are the uses of the oracle. This is the first use of OX, and this is the last use of OX. And these U's are other unitaries that are independent of the input x. So as I said, in this game, the only thing we charge for is the number of times you read the input x. So the unitaries U0, U1, they don't matter. I mean, they can be arbitrarily complicated. You're not being charged for that. The only thing you're being charged for is how many times OX appears in your quantum circuit. So a quantum algorithm, a quantum query algorithm for a function f, will use OX a bunch of times, and at the end of the day, it'll output something. And I'm denoting that by making a measurement on the output, the first qubit of the output state. And what we want is the output qubit, when measured, should be the correct answer, f of x, with high probability. Or with low error. In this case, I'm saying the error should be less than a third. The exact constant 1/3 is not really important. It's just any constant less than half would give you essentially the same model. And Q of f will denote the quantum query complexity of a function. And we use other symbols like this to denote other computational models. For example, D of f will denote deterministic query complexity, and R of f will denote randomized query complexity, but I won't really talk about those too much here. And lastly, before moving on, let me just comment on the distinction between total and partial functions, because these play a big role in query complexity. A total function is a function of the form that I talked about earlier. It's just a function in n bits. It's defined on all of the 2 to the n input strings in 0, 1 to the n. A partial function is a function that's defined only on a subset of the input strings. So it's only defined on some of the 2 to the n possible inputs. And this distinction is relevant because for partial functions, we can have very large gaps between the different complexity measures we study in query complexity. So for example, you can have exponential gaps between randomized and deterministic query complexity, or between quantum and randomized query complexity. So there's a function, for example, the four-relation problem, whose quantum query complexity is 1. You can solve it with one query, but randomly you need to make something like square root of n queries. So partial functions allow you to exhibit large exponential gaps between quantum and randomized, or randomized and deterministic, or whatever pair of models you want to compare. On the other hand, there are no exponential separations for total functions, and this is because of a fundamental result that was proved almost 20 years ago now, which is that for any total function, even the classical deterministic complexity of the function is related to the quantum complexity by a power 6 relation. So at best, you can hope for a power 6 separation. In other words, if the quantum query complexity of the function is t, then the classical complexity is at most t to the 6. So you can't have too large a gap because of this relationship. Okay, so that was a quick overview of query complexity. I hope that made sense. And let me jump to my title. So my title has 3 phrases: quantum distinguishing complexity, zero-error algorithms, and statistical zero-knowledge. And let me start by saying a little bit about zero-error algorithms. So a zero-error quantum query algorithm is very similar to the quantum algorithms I was talking about before. So those algorithms would be called bounded error algorithms because the error is bounded by some constant. It was like a third in my example. A zero-error algorithm, as the name suggests, won't have any error, so it won't give the wrong answer, unlike the algorithms I was talking about before. So what's a zero-error algorithm? It's a quantum algorithm that's allowed 3 possible outputs. Okay. The first kind of output it can say is it can output 0. So this is great. When it outputs 0, it means f of x is equal to 0. It can output 1. In this case, it means f of x equals 1. So this is where the name zero error comes from, because when the algorithm says the answer is 0, the answer really is 0. When the algorithm says it's 1, the answer really is 1. There's no errors. But there's a third possible option, which is it can output question mark. And this means it doesn't know what the answer is. If you're too young to know what that emoticon means, this is an emoji version of that. So it just means the algorithm doesn't know what's going on. But it's zero error. So when it doesn't know the answer, it'll admit to not knowing the answer. It'll never give you the wrong answer. One thing to note is the algorithm cannot just output question mark all the time, because otherwise the model will be trivial. So formally what we require is that the algorithm outputs question mark with probability at most a half. So that's the formal definition. Zero error quantum query complexity is the minimum number of uses of the oracle, so that the quantum circuit either outputs the correct answer or outputs question mark, which should output question mark with probability at most a half. And it's denoted Q0 of f. And there's a small technicality, which is that different authors define zero-error quantum query complexity differently. There's some authors define it to be self-certifying and some don't. So let me just explain what that is. It's not going to be relevant for this talk. You can use either definition for the stuff I talk about. But let me just explain what this concept is. A self-certifying zero-error quantum algorithm is one that, in addition to outputting the answer, let's say 0 or 1, it also outputs a certificate or a proof telling you that the answer is, convincing you that the answer is what it claims to be. So if it says, for example, the answer is 1, it's also going to output a set of bits. It's going to say, for example, it's going to output x1 equals 1, x3 equals 0, and x7 equals 0, such that if you query those 3 bits, you are now convinced that the answer is indeed what it claimed to be. So that's what a certificate is. It's a collection of bits. If you read those bits, you're now convinced of what the answer is. Like, it doesn't matter what all the other bits are set to. These bits will uniquely determine what the f value of the input is. So, of course, if an algorithm outputs a certificate, then it's a zero-error algorithm because you can check the certificate and you can, you can know for sure that the answer is correct. So that's a property you might also independently require from your algorithm. Anyway, so it's a bit of an aside. All right, so how does zero-error compare to the other stuff I've talked about? So one thing, which is kind of trivial to say, is that zero-error is nicely sandwiched between bounded error quantum query complexity and deterministic classical algorithms, kind of for trivial reasons. The second inequality is because, of course, a quantum algorithm can always mimic a classical algorithm. So you can always just take a deterministic algorithm and do the same thing quantumly, and now it'll be a zero-error algorithm. Okay, that's kind of trivial. And the first inequality is because a bounded error quantum algorithm can just run the zero-error quantum algorithm. And if it gets a question mark, it can just output a random bit, and that'll be correct with high probability. So, okay, this is trivial. There's nothing interesting going on so far. This is the relationship I talked about a couple of slides ago. This is why for total functions, you cannot have large separations between quantum and classical. There's always a sixth power relationship between the two. And from these two inequalities, we get the following relationship between zero-error and bounded error quantum algorithms. So let me just say that slightly differently. What this means is if you have a bounded error quantum algorithm that makes t queries, you can get rid of the error. You can come up with a zero-error algorithm, but it'll make t to the 6 queries. So you made more queries, but your algorithm now doesn't have error. And this was the best known relationship between these two measures prior to our work. And the first result of this work is to show that, in fact, there's a better relationship. We make the 6 into a 5. I mean, it's not such a big change, and it's not terribly interesting that the 6 became a 5. It's just that this is the first non-trivial upper bound on zero-error quantum algorithms that didn't already follow from an upper bound on deterministic algorithms. So this means we're using some property that's unique to zero-error algorithms. It's not just some property being inherited by deterministic algorithms. And in fact, this algorithm is pretty simple, and I can show it to you. So, okay, yeah, if you see a statement like this, for any function f, this relationship holds. How do you imagine a statement like this would be proved? One reasonable way to prove it is you assume a optimal algorithm for this guy over here. You assume an optimal bounded error algorithm that makes t queries, and you construct a new algorithm that will be zero error, and it makes t to the 5 queries. So that's a constructive proof of this claim. And I'll show you what the algorithm is. It's very straightforward. So just as a reminder, this is what the bounded error algorithm looks like. Has a bunch of queries, oracle calls. And recall that's what the oracle is. It accepts an input, an index I and a bit b, and it responds with I and b XOR to the value of x sub I. And the zero error algorithm for f is pretty straightforward. So as I said, let's assume we have some optimal bounded error quantum algorithm for the function. Let's call it A. And it makes t queries, and t is q of f, the bounded error query complexity of the function. And now my algorithm is the following, my zero error algorithm. It's going to repeat steps 1 to 3, t to the 4 times. Okay, that's easy. So what are these 3 steps? The first step is pick a random time between 1 and capital T. Okay, so you recall that t is the number of queries that the bounded error algorithm makes. All right, so pick a random time. Then run the bounded error algorithm that you have until this time. So don't make the tth query, run it until that time, then stop and measure the query register. So let's say this is the oracle call that you're at. So you stop it before it hits this point. And before you query the oracle, the input has 2 parts. There's the index register and this bit b. Measure the index register. So you'll get some index I. And step 3 is write that down. So write down I and write down x sub I. And that's it. That's the algorithm. So there's 3 steps. Pick a random index, run the algorithm, write down the index you see. And let's analyze the cost. Step 1 doesn't cost anything. You don't need to make queries to pick a random number. Step 2 might cost at most t queries. And step 3 costs 1 query because you're just querying x sub I. So in total, this algorithm makes at most capital T queries, like steps 1 through 3 make capital T queries, and then you're repeating this t to the 4 times, so that's t to the 5 queries. So that's the budget we had. We had t to the 5 queries as our budget. And why does this algorithm work? The claim is just that the stuff you've written down, which is these pairs I comma xi, in fact form a certificate for the input x with high probability. So what you do is you've written this stuff down, then you check if it's a certificate or not. This doesn't cost any queries. If it is a certificate, that's great. Then you say that's the answer. And if it's not a certificate, then you output question mark. So that's the zero error algorithm. So it's a pretty simple algorithm. I won't explain why it works, but I just wanted to highlight the algorithm itself is very easy. Okay, so that's what I wanted to say about zero error algorithms. Yeah, as I mentioned, my title had a bunch of different phrases. And quantum distinguishing complexity is really the theme of this work. And in fact, the previous result that I talked about, it didn't mention quantum distinguishing complexity explicitly, but that's really what goes into the proof. So let me say a little bit about what quantum distinguishing complexity is. So a quantum distinguishing complexity algorithm or quantum distinguishing algorithm is like a quantum query algorithm, except it's a little weaker. It's weaker in the sense that for a quantum query algorithm, what we need is the output state, let's call it psi x, the algorithm's output state. If I measure the first qubit, it's either 0 or 1 with high probability, indicating whether the function is 0 or 1. Whereas for a quantum distinguishing algorithm, all we require is that this output state psi x distinguishes inputs with different output values. So if psi x is the state for an input with output 0, and psi y is the output for a y with f of y equals 1, then psi x and psi y just need to be distinguishable. And what that means for quantum states, for 2 quantum states to be distinguishable, is that they're far apart in some distance measure, like trace distance, or in other words, their inner product is small. So that's all we require. It's a weaker requirement than what's required for a quantum query algorithm. And this is the formal definition. I mean, it doesn't really matter, but it's just saying that for inputs x and y with different function values, the inner product between their output states should be low. So as I mentioned, this is a weaker requirement than quantum query complexity, and therefore this measure can be smaller than the quantum query complexity of a function because, of course, the output state at the end of a quantum algorithm is distinguishable for yes and no inputs because you can just look at the first qubit, and the first qubit will be 0 with high probability in one case and 1 with high probability in the other case. So they're certainly very distinguishable states. But all we require here is that they're distinguishable, not that they specifically are 0 or 1 in the first qubit. And if you work in query complexity and you've heard of randomized sabotage complexity, then fun fact, this is the quantum analog of that measure. If you haven't heard of it, it doesn't really matter. All right, so I just wanted to mention that this measure really is different from quantum query complexity in the sense that for partial functions, you can have an exponential separation between this and quantum query complexity. And the collision problem is an example that exhibits this. Maybe I won't get into the details of what the collision problem is, but if you know what it is, then the quantum complexity of this problem is high. The regular quantum query complexity is n to the 1/3, but the quantum distinguishing complexity of this function is just 1. You can do it with one query, and this is the solution, but I won't explain why it works. What we don't know in this work is whether there's any total function with a gap between these two measures. So this was a partial function. As I said before, life is usually much easier with partial functions. You can always exhibit large exponential gaps. For a total function, we don't know if there's any gap between these two measures. And the connection with the previous result is that what we actually prove is that for any total function, the zero error complexity is upper bounded by this quantum distinguishing complexity to the power of 5. And because this is smaller than just regular quantum query complexity, that's how we get the fifth power relation between the two measures. But the proof actually involves this quantum distinguishing complexity. The other thing I wanted to mention about quantum distinguishing complexity is how it compares to other lower bound techniques on quantum query complexity. So there's two big ones, which is the adversary method and the polynomial method. So it turns out that quantum distinguishing complexity is better than the adversary method, or like the old adversary method, which doesn't completely capture quantum algorithms. If you know what that is, if you don't, it doesn't really matter. But one reason this relationship is interesting is because this explains some of the limitations on the adversary method. So for example, we saw before that the collision problem had quantum distinguishing complexity 1. This means that the adversary method also cannot prove a bound larger than 1 for the collision problem. So if you want to prove a lower bound on the quantum query complexity, you cannot use the adversary method. So that's one nice thing. The other thing we show is that, in fact, this can be far superior to the adversary method in some cases. So for a total function, it can be as much as quadratically bigger. For partial functions, it can be exponentially bigger. The other commonly used lower bound technique for quantum query algorithms is the polynomial method. For that, we don't know if our measure is bigger or not. So we don't know if quantum distinguishing complexity is always bigger than the approximate degree of a function, but we can show a fourth power separation even for a total function. All right, so that's kind of all I wanted to say about quantum distinguishing complexity. And I do want to, before ending the talk, just say a few words about statistical zero knowledge. So this is a topic that would take a lot of time to get into, but I wanted to say a few sentences just because I think zero knowledge is one of the gems in theoretical computer science. It's a really beautiful idea. And so let me just tell you what a zero knowledge proof system is. So a zero knowledge proof system is, you want to imagine this as a conversation between an algorithm, Arthur, and an all-knowing prover, Merlin. Merlin knows something. Let's say Merlin knows the value of the string x that you're querying, and Merlin wants to convince you that f of x equals 1. Now you have a little conversation with Merlin, like a polynomial time conversation, and it's a zero knowledge proof system if the conversation satisfies three properties. First, if f of x is 1, there should be some way for Merlin to convince you that this is the case. Okay, that's reasonable. That's what a proof system would mean, that Merlin is able to convince you of true facts. Also, it's a sound and valid proof system, which means that if f of x is 0, then Arthur should not be convinced that f of x is 1. So Merlin shouldn't be able to convince you of false things. So that's fine. This is just the definition of a proof system. The really interesting part is that the zero knowledge requirement, which says that Arthur learns nothing else from this interaction other than the value of f of x. So Arthur didn't know what f of x was at the beginning of the interaction. At the end of the day, maybe Merlin has convinced Arthur that f of x equals 1. And so Arthur has learned something new. But other than this one bit of information, Arthur should not learn anything else. So that's what zero knowledge refers to. Yeah, so unfortunately I don't have time to get into details of how this works and how you define zero-knowledge proof systems in the query setting. For those of you who are familiar with this, I'll just say that the way we define this in query complexity is through its complete problem, which is quantum state distinguishability. But okay, if you don't know what that is, doesn't matter. Okay, and why did we talk about this? And the reason we talked about this is if you define quantum statistical zero knowledge in the query setting, it turns out to be nicely sandwiched between all of the measures I talked about today. So it's in between quantum query complexity and quantum distinguishing complexity. So now you have this relationship at the bottom between these four guys. And what's really nice about this relationship is this allows you to prove lower bounds on this measure QSCK. And also this will let you prove oracle separations against the complexity class QSCK. So if you know what that is and you know what oracle separations are, this finally gives us a handle on proving oracle separation for QSCK. But if you don't, that's fine too. Since I'm running out of time, maybe I won't tell you the implications for communication complexity, but we have a bunch of implications to how you can prove lower bounds in communication complexity, and this area is called lifting theorems. So what this means is, what this does is it connects a lower bound in query complexity with a lower bound in communication complexity, and you say that the lower bound has been lifted using a gadget, and essentially what we show is if you can prove lifting theorems for the zero error or the distinguishing model, then you get one for quantum query complexity for free. All right, that's all I wanted to say. Yeah. Thanks.
Could you have any relation between quantum perfect zero knowledge and Q0 that you defined, like that you studied as well?
Perfect zero knowledge. So you mean, okay. I'm not sure. I don't think anyone has studied that in the query setting. Yeah, I have no idea. I mean, yeah, as far as I know, no one studied computational zero knowledge in the query setting either, or the communication complexity setting. These are just new things we tried. Yeah.
Okay. Other questions? Okay, so you have a question. So can you give a few explanations about how do you prove your lifting theorem? Is it easy to describe in a few words?
The lifting connection? It's, maybe it's not the easiest thing to describe it in a few words, but what we show is this complexity measure QD. Let's say maybe that's the easiest one to work with. Has a curious property. So for most complexity measures, if you compose them with an easy function, the complexity measure will only go up by a little bit if it does go up. QD can jump abruptly. So you can compose it with a small function that has low complexity, but it can jump from whatever it was all the way up to quantum query complexity. Mm-hmm. So, and we show, for example, that if you compose it with the index function, which is just like, or the address function, it jumps abruptly from wherever it was, even if it was, let's say, 1 for the collision problem, and you compose it with the address function, it'll suddenly jump to n to the 1/3, which is its quantum query complexity. So what we're able to do is use this to relate the quantum distinguishing complexity of a function with a gadget, and we throw this indexing also all into this communication lifting gadget. And this kind of shows that if you can do something with QD, in some sense you can make it work for Q just by throwing in a little bit extra, by throwing in this little indexing gadget. And then we have to do a little bit of work to get rid of the fact that we use this indexing gadget because we want the result to hold for the same communication gadget. But I'd say the key idea is just this indexing gadget really changes the quantum distinguishing complexity of a function, but it does not change the quantum query complexity of a function other than by a log factor.
Okay, thank you. So I think it's time so we can thank Robin again.